GoldFinch, high-performance RWKV transformer hybrid with linear prefill and extreme KV cache compression. Daniel Goldstein. Fairs Obaid, Eric Alcade, Guangyu Song, and Eugene Che. Abstract. We introduce GoldFinch, a hybrid linear attention transformer sequence model. It uses a new technique to efficiently generate a highly compressed and reusable KV cache in linear time and space with respect to sequence length. GoldFinch stacks our new GoLD transformer on top of an enhanced version of the Finch RWKV6 architecture. We train models with up to 1.5 billion parameters of the Finch, Llama, and GoldFinch architectures and found significantly improved modeling performance relative to both Finch and Llama. Our cache size savings increase linearly with model layer count, ranging from 756 to 2,550 times smaller than the traditional transformer cache for common sizes. This enables inference of extremely large context lengths, even on limited hardware. While autoregressive generation has ON time complexity per token due to attention, prefill computation of the entire initial cache state for a submitted context costs only O1 time per token due to the use of a recurrent neural network to generate this cache. We release our trained weights and training code under the Apache 2 license for community use. Introduction. Variations on linear attention have proliferated in recent research, approaching the performance of traditional multi-headed, scaled dot product attention while achieving lower inference costs. In MHA, the model's effective memory is bounded by its context length, with the attention calculation resulting in quadratic time complexity with regard to that length. Conversely, most forms of linear attention can be computed recurrently in O1 time per time step, instead of inspecting the entire context length to generate each new token. Recurrent linear attention uses a fixed size hidden state that is updated at each time step, functioning as its memory of the past. The limited size of this state constrains the capacity of this memory. The success of large language models has motivated interest in ultra-long context length language models. For example, Gemini Pro offers a window length exceeding 1 million tokens. However, these extra-large context lengths come with large associated costs due to the need for MHA to examine every prior token within the context when generating a next token. Although a naive inference implementation would recalculate every key and value at every layer in a traditional transformer, it is common practice to store these in a key-value cache and retrieve rather than recompute them. KV cache memory costs can be very high. For example, a 1 million token cache for an 80-layer traditional transformer model of hidden dimension, 8,192, would take up over 2.5 terabytes at bflow-16 precision. We focus on reducing the memory costs of this cache while also reducing computational complexity and memory usage for processing the initial context of a request. Our contribution is the combination of several innovations to create the GoldFinch architecture, which improves pre-fill and decoding efficiency, as well as downstream modeling performance, and introduces the following innovations. Employs a novel parameter-efficient modification of Finch, RWKV6, which we call Finch C2 for the first two-thirds of its layers. Uses the output of these Finch C2 layers to produce an extremely small compressed global key cache, using a novel mechanism we call TokenCat. Our cache thus requires only 1/16 of the model per token plus the original input token indices. Instead of twice the model per token for traditional KV caches, employs a novel modification of the traditional transformer architecture, which we call GoLD, for the last one-third of its layers to consume this key cache and produce outputs without even requiring a traditional value cache. The GoLD layers and key compression. The GoLD layers are an adaptation of a novel improved transformer we call GPT-alpha that can also be used as a standalone transformer model for improved non-hybrid performance. This new architecture brings a series of significant benefits. We are able to reuse the same KV cache on every transformer layer while maintaining greater than Llama performance. This reduces the KV cache size by a factor of the total number of layers of the model. We eliminate the values from the KV cache, leaving only a key cache. Instead of catching values, we store the input indices and generate the values from these, reducing the KV cache size by another factor of nearly 2. We are able to compress our key cache by applying a form of low-rank adaptation, LoRa, to the output of a single layer, and re-expanding the compressed version by concatenating the compressed version with the original token embeddings, further reducing the size by 128 times. We use the input embedding table and RWKV style token shift to generate values for attention without sacrificing performance. By using Finch C2 blocks at the start of the model, the key cache automatically encodes the underlying implicit positional representation, thereby removing the need for positional encoding within our transformer layers for trained context lengths. We still require an additional positional encoding method for extrapolation to new context lengths unseen during training. There are many use cases of LMS that involve relatively short responses to questions about long documents. Because our compressed key cache is generated by an RNN with an operating time and space complexity of 0.01 per token with regard to sequence length, we are able to generate the cache in these cases extremely inexpensively and apply the ON per token cost GOLD transformer portion of our calculations only to new token generation, for which relatively few iterations are often required. Finch C2 architecture improvements. To obtain our Finch C2 architecture, we improve the Finch time mixer by removing the gate, swapping out group norm for a layer norm across all heads, doing a new multiplication of the key by 1 minus the decay to keep the KV state rows normalized, and replacing Finch bonus term with a new data-dependent separately token-shifted second value. These changes result in improved performance with little to no speed penalty and significantly fewer total parameters. To obtain our GPTalpha architecture, we improve the Llama architecture by replacing the transformer feed-forward network with the RWKV channel mixer, and adding RWKV-style token shifts and extra layer norms to attention layers. Both Finch C2 and GPTalpha can be used either as standalone model architectures with improved performance over their counterparts, or as part of the GoldFinch hybrid model architecture. GoldFinch model training and evaluation. We trained GoldFinch models up to 1.45 billion parameters on 1.5 trillion tokens of Minipile and compared them to slightly larger equivalently trained Finch and Llama models. We found that GoldFinch significantly outperforms both Llama and Finch in downstream performance and perplexity across nearly every benchmark we tested, while maintaining fewer parameters, a much smaller cache than Llama, and perfect MQAR recalled due to its use of full attention. Background. Transformers have become the de facto choice for most sequence modeling tasks, and have been shown to be especially effective in the context of language modeling. However, they present computational challenges when processing long context lengths, which has hindered their adoption for long sequence tasks. Specifically, the formulation of multi-head scaled dot product attention has a computational complexity of O(n) squared with respect to context length. Additionally, inference engines typically rely on the use of a KV cache to enable autoregressive token generation in O(n) time per token. This cache grows linearly with context length and becomes challenging to fit into limited video random access memory for longer sequences. Recent transformer models such as the Llama series rely on grouped query attention to help reduce this cache size problem. At a typical number of groups, GQA reduces the KV cache size by a significant factor, which is helpful, especially on consumer-grade hardware, but leads to a reduction in downstream performance, and longer sequences still cause a significant problem in terms of VRAM usage. The recently proposed YOCO improves the computational complexity for pre-fill of the initial request context, and also reduces the KV cache size by introducing a new global KV cache instead of the usual per-layer cache. The computational improvement is achieved by replacing the first half of the layers in the model with linear attention-based RetNet G layers, which is a recurrent neural network architecture that requires only linear time with respect to sequence length. YOCO stores the output of these first layers as a global KV cache, which is then used by the second half of the layers, featuring multi-head attention. Overall, this reduces the KV cache size by a factor of the number of layers, without a reported performance reduction. Method. GoldFinch follows the general structure of the Finch architecture. which is also the common prenorm decoder transformer structure used in Llama and RWKV. It consists of a series of layers, each containing a time mixing sublayer followed by a channel mixing sublayer. All channel mixing sublayers are Finch channel mixers. The following formulae describe the three varieties of GoldFinch sublayers. All matrices are learned per layer, unless described otherwise. We show all time mixing formulae per head for conciseness, except the formulae for those layer outputs where heads are combined via concatenation. Model dimension is denoted as D. Head size is H, and number of heads as N. Finch C2 time mixing. The first 2/3 of time mixing sublayers use a variation on the Finch time mixer we call Finch C2-RE. We customize the Finch time mixing sublayers by removing the gate, swapping out group norm for a layer norm across all heads, and doing a new multiplication of the key by 1 minus the decay. Finally, we replace Finch's bonus term with a new data-dependent, separately token-shifted second value, computed using the same weights as the base value, with an additional LoRa added to the result. We find that this allows us to remove all of the gate parameters while retaining performance. GoldFinch key compression. The output from the first 2/3 of the model is used in two ways. It is passed on to the next layer in the usual manner and also compressed down via multiplication with the global, not per layer, learned matrix to 1/16th, its original size, and stored into a unified single-layer compressed key cache. GoldFinch key decompression, token cat. The compressed key cache is decompressed via a two-step method. The step is token cat, short for token concatenation, in which the compressed key is concatenated with the original input token, embedding from the very beginning of the model. The concatenated result is then multiplied with the global, not per layer, learned matrix, and RMS norm to obtain the decompressed attention protokeys, which are common to all GOD attention sublayers. GoldFinch attention time mixing. The remaining time mixing sublayers are a variation on GP-alpha attention sublayers employing MHA that we call GoldFinch attention. Each GoldFinch attention sublayer calculates its own unique attention keys and values from the decompressed protokeys and the original input token embeddings, respectively. Each is passed through a data-dependent token shift, with the result passed through an additive LoRa. GoldFinch channel mixing. GoldFinch channel mixing is identical to Finch channel mixing. It is used as the feed-forward network component on all layers of the model. Both Finch C2 and GoldFinch GP-alpha time mixing. For completeness and to show how it can be used in a pure transformer architecture, we list the formulae for GP-alpha time mixing when not used in conjunction with TokenCat below. Experiments. We trained 1.5 billion parameter class models with 24 layers, 2048 hidden dimension, 2048 context length of Finch, Llama, and GoldFinch for comparison on Minipile, all using the same RWKV world tokenizer. GoldFinch ends with dramatically lower final loss than the others, and uses over 100 million fewer parameters than its Finch counterpart. We additionally trained a GoldFinch with no compression, to show that there is very little lost with our choice of a 16:1 hidden dimension compression ratio. In addition to comparing training and validation losses, we ran a series of common benchmark evaluations on the three 1.5 billion parameter class models trained on Minipile. Finch and Llama scored similarly to one another, and GoldFinch significantly outperformed both. Ablation studies. We ran various smaller-scale ablation studies to determine the contributions of different parts of the GoldFinch architecture relative to both Finch, Llama, GP-alpha, and a hybrid of our improved Finch and GP-alpha, with no KV cache compression or key value sharing. The new second value added in Finch C2 had the smallest positive impact of anything measured. Surprisingly, GoldFinch performed very slightly better than even the Finch C2 GP-alpha hybrid, with no KV compression at all. Associative recall. Associative recall is a synthetic task designed to emulate the human ability to associate and retrieve information. It evaluates a model's skill in recalling previously mentioned information within a given context. Previous studies suggest that a model's performance in associative recall is a good indicator of its efficacy in in-context learning. Consequently, associative recall has been employed as a benchmark for developing new language model architectures. GoldFinch achieves perfect multi-query associative recall scores, outperforming traditional attention-free language models. As a hybrid architecture that leverages attention, GoldFinch can solve multi-query associative recall as well as transformer models with attention. Additionally, we trained GoldFinch on a context length of 1024 to demonstrate that this trend continues. Long context experiments. We tested the loss of our small finch and GoldFinch models, pre-trained on Minipile, at all context lengths up to 65,536 on the P918 dataset of older books. These pre-trained models were all trained at only 1,024 context length. The Finch model is able to maintain a fairly low loss throughout the 65,536 context length. The base GoldFinch model trained with no positional encoding goes up in loss significantly starting at around double the trained context length, then plateauing at a high loss. The GoldFinch model trained with rope on its GOLD attention sublayers performs better, but loss still increases somewhat as the sequence progresses. However, by applying interpolated rope values, we are able to obtain low loss throughout the extended context length. We conclude that for GoldFinch models in which extrapolation beyond the maximum trained context length is desired, the GOLD attention sublayers should be trained with rope with interpolation employed upon inference. We then fine-tuned the rope and non-rope models mentioned above on 165 million tokens of Minipile at longer context lengths. During this fine-tuning, we froze the entire RWKV portion of the model up to the first GOLD layer, allowing the optimizer to update the parameters of only the GOLD layers and output head. This saves a significant amount of time and VRAM during fine-tuning, allowing an even longer context length to fit into memory and using roughly 3 times fewer FLOPS per token. We theorize that because the GOLD attention portion of the model can use keys generated from the RWKV output, this is enough to support sophisticated attention matching across the entire context length. Our experiments showed that indeed, the rope model with GOLD layers fine-tuned at longer context lengths exhibited significantly lower losses against P19 up through those lengths and even beyond. On the non-rope model, this process was somewhat successful within the fine-tuned context length, while still failing at extrapolation. This was unexpected, since the RWKV layers were not updated, and the GOLD layers included no positional encoding mechanism. We postulate that token shift may supply some minimal positional information to the model. Checkpoint upgrade training. We have attempted upgrading existing pre-trained Finch models to a more limited version of GoldFinch that uses the Finch architecture for its RWKV layers instead of the Finch C2 component. We tried many variations on 2 methods. One that adds new GOA layers on top for a total of around 11% more parameters, and another which keeps the layer count the same as the pre-trained model. Thus far, with only small amounts of upgrade training, neither method has performed to our satisfaction. Both methods were attempted on a 1.6 billion Finch checkpoint that had been pre-trained on 2.5 trillion tokens. For the first method, we appended 4 GOLD layers on top of the pre-trained 1.6 billion Finch checkpoint before the language modeling head, and continued training it for 100 million tokens using 2 different learning rates. The original 24 pre-trained layers were kept at the same learning rate at which their pre-training had ended, while the learning rate for the 4 new GOLD layers was annealed along a cosine schedule from a high learning rate to the original rate. While the performance of this model was in line with the original model, it was unclear if the resultant model from this method really learned anything of value in its GOLD layers. The second method involved freezing the embedding and RWKV layers and importing, but not freezing the final 1/3 of the channel mixer sublayers that were paired with freshly initialized GOLD attention sublayers. We then trained this model on a relatively small amount of data while annealing the learning rate to the final learning rate seen in the pre-trained base model. The resultant model obtained a similar validation loss on Minipile to the base model, despite being trained on a completely different dataset and the base model having been already trained for over 2.25 trillion tokens. However, the new model's LAMBADA scores were worse. We attribute this loss of performance to the brain surgery required to keep the layer count the same, in which we effectively erased the Finch time mix parameters in the upper one-third of the model. We are still doing further experimentation on these upgrade methods to see just how well they can be made to perform. We hope to be able to inexpensively upgrade even the largest 14 billion Finch model to this reduced GoldFinch format, and see significant performance improvements at larger context lengths due to the GOLE attention being able to look back across the entire context with no state size-based memory limitations. Further work. We anticipate updating this preprint with further studies as results become available, including checkpoint upgrade results and evaluations, longer experiment training runs, and new long context experiments. Please check back for updates. Most of the experiments done for this preprint were performed over a short period of time on a single node containing 8 RTX 4090 cards. In the future, we hope to demonstrate GoldFinch's performance on larger models with significantly more tokens. We expect that GoldFinch will work similarly with other linear attention and SSM architectures in place of the Finch C2 blocks. For example, it should be possible to implement a GoldMamba architecture in the same style. Further work might explore increased memory reduction for the global KV cache via quantization, and application of ring attention to lower the memory requirements when extending to very long contexts. As a hybrid architecture model, GoldFinch will likely benefit from any future improvements to the RWKV and Transformer architectures. Conclusion. We have introduced a hybrid RNN attention model architecture, GoldFinch, and trained models that demonstrate its performance up to 1.45 billion parameters. The resulting hybrid RNN attention models combine the efficiency of RNNs with the capabilities of attention-based models. Having RNNs for the initial layers allows for fast pre-fill and removes the need for positional encoding on the RNN layers, while the attention layers improve associative recall. The combination with a highly compressed global KV cache unlocks a memory reduction in inference while maintaining enhanced performance. We release the trained weights and training code under the Apache 2 license. Acknowledgements. Special thanks to Bo Peng for his tireless dedication to the RWKV architecture and community. The main GoldFinch code herein was based on a modified version of his public linear attention arena code repository, and upgraded models were based on his pre-trained Finch model releases.